In this video, we're going to learn about direct and inverse variation functions. Now, variation functions can be written as you can see in the yellow highlighted, which is basically going to be a number times x to the power of another number. So this is a form of a polynomial function. Because we're going to have a certain exponent, which is going to be a number. Now, what you'll notice with variation models is that we're not going to have a plus or minus another value, which is the case in our normal polynomial functions such as quadratics and cubics. Variation models are only going to be a number times x to the power of another number. Now, this value of n, the exponent, can either be positive or negative. And depending on if it's positive or negative, it's going to make the variation model look very different. First, we're going to talk about the direct variation. The direct variation is when our value of n is positive. So here we could have an example such as 3x to the power of 2, which would technically be a quadratic function. We could have 5x to the power of 3, and so on and so forth. So all of these are examples of direct variation. What we'll notice is that for all of them, they are passing through the origin. So the point 0, 0 is a point that it will always be a point for a direct variation. And that's because of the concept that we don't have a plus c. So the origin will be a point on every direct variation function. Now, if we look at n, the exponent being negative, this is going to be an inverse function. So we could have something like 3x to the power of negative 2. Another way we could write this is 3 divided by x squared. So if we have x to the power of negative 2, or we have x to the power of 2 in the denominator, these two are equivalent using our exponent rules, right? And both of these represent inverse variation function. And since we have x in the denominator, well, we now are going to have a horizontal and vertical asymptote. So technically, the horizontal asymptote, this is going to be when y is equal to 0. So our horizontal asymptote is going to be when y is equal to 0, while our vertical asymptote, maybe I can choose a different color, our vertical asymptote, this is when our denominator is equal to 0, which seems to be happening when x is equal to 0. So for inverse variation functions, we now have two asymptotes created. A vertical one when the denominator is equal to 0, and we also have a horizontal asymptote. And we're going to practice with these two types of functions. First, let's start with a direct variation for practice. Like we said, a direct variation is going to be of the form where we have x to the power of 3 or x to the power of 2 or even x to the power of 1, right, which we just forget. All these are examples of direct variation. A direct variation is two variables that are directly proportional or vary directly if multiplying one of them by a number results in the other one being multiplied by the same number. So it always passes through the origin. That's what we mentioned here, right? So these are examples of direct variation. If y is directly proportional to x, then we can write it as follows, where we have our two variables, and this symbol in between is the symbol for directly proportional. It's basically like an infinity sign, but it's missing kind of half of the second loop. And this symbol is going to be used for directly proportional. If two variables are directly proportional to each other, that means we can take one variable, multiply it by a number, and it's going to give us the other variable. So that means that I can write down my equation for directly proportional as y is equal to a number times x, because x and y are directly proportional. And we'll practice this with examples. So let's do an example. Suppose that p is directly proportional to t, and that when p is equal to 17, t is equal to 5, find t when p is equal to 60. So first, let's deal with the fact that p is directly proportional to t. That means I can create an equation such that I have p times a number k, which is equal to t. I can find what this constant is, this constant of proportionality, by substituting the value of p and the value of t, which is basically a coordinate in my equation. On my calculator, I can go into NSolve, and I can find what is the value of k. So 17, and then we have x times 5, and we're going to get that the value of x, or k in this case, is 3.4. So that means that the function that exists between p and t is that p is equal to 3.4 times t. So we're looking for t when p is equal to 60. So 60 is equal to 3.4 times t. Again, we can go into numeric solve. We have 60 is equal to 3.4 times x, and we get that t is equal to 17.6. Now let's try another one. Suppose that d is directly proportional to z squared, and that when d is equal to 14, z is equal to 5. Find the following. Before we can even start by solving these questions, we have to find what is the equation that connects d and z together. So if d is directly proportional to z squared, then I can create this equation here, and I can find what the constant is. So I have 14 is equal to z times 5 to the power of 2. Into your numeric solve, we can find the value of k, and we get that k is equal to 0.56. So the equation connecting the two of them is d is equal to 0.56 times z squared. So for part A, find d when z is equal to 15. Then I can replace z by 15 in my equation, and I get 126. Next up for d, I'm looking for z, and I know that d is 140, so 140 is equal to 0.56 times z squared. Now at this stage, we have a quadratic, right? So there's going to be actually two values possible for z. So if you use numeric solver, that's okay. It's going to give you only one possible value. So I'd probably recommend that you graph it instead and find the intersection point. So onto my graph, I'm going to try and find the intersection point. So I'm going to go zoom fit, which is option 0. I still don't see enough of the x boundaries. So my x minimum is not large enough, and my x maximum is not large enough. That seems better. So I'm going to go ahead and find the two intersection points. Second function trace intersection. First curve and second curve, and then I'm going to go and find the point towards the left, and I get that one intersection point is when x is equal to negative 15.8. And then I'm going to repeat the same process for the other one. Since it's a direct variation, then we are expecting to get the exact same value, however, with a positive value. So we should have positive 15 for the intersection point because it's the symmetry of our quadratic function. Now they're telling us that they only want the answer such that z is bigger than 0. So that means we're not interested in the first one, and we're only going to give the second one as our answer. I'm going to change this to a z. Now if we compare this to inversely proportional, well, two variables are inversely proportional or very inversely if when one is multiplied by a constant, the other is divided by the same constant. So here are some examples of inverse variation. So we have y is equal to a over x. This is equivalent to y is equal to a times x to the negative 1. Y is equal to a divided by x squared, or a times x to the negative 2, right? So it's a negative exponent here. And if y is inversely proportional to x, then we can equally say that y is therefore directly proportional to the inverse of x, so 1 over x. So that means that we can write it as y is directly proportional. This is a symbol for directly proportional to 1 over x. And therefore, we're going to have the equation y is equal to a number, k, divided by x. So we're using the same notation as directly proportional, but if it's inversely proportional, we take this variable and we put it into the denominator. And we're going to practice with a few of these. Now let's look at an example for inversely proportional. So y is inversely proportional to x. So that means that I can write y is proportional to 1 over x. That's an equivalent way of writing it. So that means I can create an equation such that we have y is equal to k divided by x. When y is equal to 12, x is equal to 10. So I can use this to find the value of k. And I'm going to get that the value of k is 120. Therefore, the equation that exists between y and x is that y is equal to 120 divided by x. And I'm going to be using this to answer part A and part B. Find y when x is equal to 40. So 120 divided by 40, we're going to get that y is equal to 30. For part B, find x when y is equal to 19. So we have 19 is equal to 120 divided by x. So we can go into numeric solve. And I get that x is equal to 6.32. Rounding this to 3 significant figures. Good. Next example. Suppose that p is inversely proportional to the square of n. So the square of n. So now we have an equation where we have p is inversely proportional to the square of n. So p is going to be equal to a number divided by n squared. I'm going to use the fact that when p is equal to 40, n is equal to 6 to find this value of k. So I have 40 is equal to k over 6 squared. Into my numeric solve, and I'm going to get that this value of k is 1,440. Therefore, the equation that exists between p and n is that p is equal to 1,440 divided by n squared. So I can find my answers. Part A, find p when n is equal to 12. So we replace n by 12. And we can find our value for p. So p is equal to 10. And then for part B, we're now looking for p. So given that n is bigger than 0, find n when p is equal to 90. So 90 is equal to 1,440 over n squared. Now again, since there's a squared here, there's going to be 2 possible answers. So we're going to do a graph in order to find the 2 intersection points. So 90 is going to be one of the functions, and the other function is going to be the inverse function, which is going to be 1,440 over x squared. I'm going to go ahead and graph this. And in fact, I do see 2 points of intersection, and I'm only interested in n being bigger than 0. So that means I'm going to go find that point of intersection that is towards the right. First curve, second curve. And then we are looking for the guessing the point. So we're going to use the point which is closest to the right. So we get the intersection point 4 and 90. So that means that n is equal to 4. Now, sometimes the questions will not be asked in this manner, but instead they're going to give us some data points. So sometimes they're going to give us some data and they're going to ask us, what is the best equation for this model? If they're asked to find an inverse or a direct variation model, we're going to be using in our calculator what's called the power regression. So this power regression is going to give you direct and inverse variation model. So it's going to basically give you a function, and a times x to the power of b. And then, of course, if this b is positive, it's going to be a direct variation. If this b is negative, an inverse variation. And let's try some questions. Example 5. A company manufactures ball bearing in different sizes. The table alongside shows the radius and the mass of each type of ball bearing. Draw a scatter plot of the data and discuss the shape of the graph. At this point, I'm going to ask you to pause the video and put all of your data into your list 1 and list 2. Once your data is put in here, then we want to see this graph. So I can go on to my stats plot, second function stats plot, and I'm going to go and turn on my stats plot, which has scatter plot as the type, list 1, list 2, and I'm fine with the marker and the color. I'm going to go on to my graph. Oh, true, I still had some functions here, so I can remove the function that I had. And I have my points here. Now, looking at this data, I see that it seems to be increasing in a curved way. So it wouldn't be linear, but it does indicate that it would make sense to cross through the origin 0, 0. So for the first part of drawing the scatter plot and discussing the shape, I would probably see that it looks like it's curved, increasing, and it seems to be passing through 0, 0. Therefore, we're going to try and obtain a power model that best fits this situation. So we're going to go on to stats, calculate, and we're going to go find our power regression, which is A. List 1, list 2 is correct. We don't have a frequency list. So if we want, we could store this by going on alpha and then calculate. We'll see that we have the option for y1, y2, and whatnot. I'm going to choose y3 because I know I have other functions in y1 and y2. And we're going to go ahead and calculate. When we calculate, we do in fact get a power regression. And in order to write this correctly on our piece of paper, we're going to have y is equal to a. We're going to round to 3 significant figures times x to the power of b. We're going to round to 3 significant figures as well. So this seems to be actually a cubic model. Now for part C, estimate the mass of the ball bearing when the radius is 22 meters. Our radius is what we used as our x, so we're going to look at what is the value of x when what is the value of y when x is equal to 22. Now the good thing about storing our function is that everything is in here already. So when I go onto my graph, I can actually ask my graph to trace, and we're not going to use the plots, but we're going to use the function. So I just had to change between the points and the function. And then when I type in 22, it's going to give me the value as if I replaced 22 into my equation. So if I would have put 22 into this equation, it would have given me 348 rounded to 3 significant figures. So this is just a shortcut with your calculator to be able to use the calculator page to help solve these questions. Let's do our final example for this video. So we have another data set, and we're told that the force between 2 positively charged spheres was measured at different distances. The result was recorded. So we have distances and force. Let's first take some time and put this into our calculator. For part A, they're asking for obtain a power model. So power model stats, calculate. We're going to go and choose our power model. We put our information as y1 and y2. And I'm going to store this into, let's say, y4, since I haven't used this one yet. And we're going to go ahead and calculate it. So our power model is going to be y is equal to 5.63, rounded to 3 significant figures, times x to the power of negative 2. Now, if x is if the value of b is negative 2, that means that we have an inverse variation. So we're ready to go and answer the next part of the question. B, estimate the strength of the force when the spheres are 0.4 meters apart. So 0.4 meters apart, that's the distance. So this is our value of x. And we're looking for what is the force when we have an x value of 0.4. So you could put this into your calculator and find it manually. Or since we have y4 to be our equation, then we can use our calculator. So if we have this beautiful graph, I can put trace, not using the plot, so I'm going to go up to make sure that I have the function, and then I'm going to have 0.4, enter, and we get that the force will be 35.2 newtons. So this is going to be the force when we have a distance of 0.4 meters. And for part C, find the distance between the spheres if the force is 650 newtons. So now we have 650 newtons is equal to our equation, minus 2. So you could put this into numeric solve if you want, or you could graph it. At this point, since I already have the graph, I would probably graph it and find the intersection points. First, I'm going to turn off my scatter plot because it's a little bit annoying to see all those points. So I'm going to go and find the intersection point between my function and 650. I'm going to put this on my graph. I don't see y is equal to 650, and that's because my window is not big enough. So I'm going to make my window even bigger, maybe 700 for the y maximum. And then I'm going to go try and find the intersection point. I noticed that my graph, there seems to be a little bit of a glitch, but I'm going to hope that my calculator can find the intersection point for me. First curve, yes. Second curve, yep. And then the intersection point, I think, is somewhere up there. And in fact, it is. And we're going to get that x is equal to 0.0931, rounded to 3 significant figures.